Today we will be constructing a computer model to try to predict the motion of an oscillating spring mass system. We will be using Newton's second law, Hooke's law, and the analyzed tracker video of a real-life oscillating spring mass system in order to do this. We will then explore further the meaning of the motion behind the oscillating spring mass system using our new principle, the energy principle. You will see that our model does a good job of predicting the motion of our system, and that we have a few qualms with the energy principle. We are given a few variables to start off with. The mass of our ball is 0.402 kilograms, the mass starts from rest, and the equilibrium spring distance is 0.7 meters. Here's a shot of our tracker video that we'll be using for this lab. In order to build our computer model, we always need to initialize our data. From our two equations that we're going to use to build our computer model, we need to calculate a few things. First, we need the spring stiffness, or K sub s. Using the definition of a period in our data from tracker, we can calculate this. By picking three sections where the mass has made a complete oscillation, we can find the average period. By plugging this into the equation already stated, we find K sub s to be 6.88 newtons per meter. Now, the second piece of data that we need is the relaxed length of the spring, L naught. We can find this using our knowledge of static equilibrium, or when the mass of on the spring is unmoving. Here, because the system is in equilibrium, we know that the two forces acting on our system, the force of the spring and the force of gravity, must be equal. From here, we can set the forces equal to each other and solve for the relaxed length. Again, notice that we are using K sub s that we solved for earlier. We have all the information that we need to create a computer model in order to try and predict the motion of our system in real life. This block of code here is simply initializing our computer code using known constants. The mass of the ball is 0.402 kilograms, and the starting point is the starting point from rest. This starting position is right before the mass begins to move. This block of code initializes our other constants that we already solved for, including the spring stiffness K sub s and L naught. Take careful note of our delta t, which is 1 over 210 tenths of a second. This block translates Hooke's law into computer code. Notice our directional vector L hat is L, mass position minus the origin, over its magnitude. Also, S describes the overall stretch or compression of the spring and is equal to L minus L naught. Now we need to initialize Newton's second law. The computer code here does that. Notice that F net here is the sum of the spring force and the force of gravity. Newton's second law is also used here to update the position of the mass after every iteration. We also need to update the force of the spring after each iteration because of the spring force is dependent on the length of the spring, and the length of the spring changes after every iteration. Let's now use our energy principle to further explore the motion of our system. The change in the energy in our system is equal to the change in kinetic energy, plus the change in the gravitational potential energy, plus the change in the spring potential energy of our system. Here, we are initializing just that, by translating the equations of each into computer code. The very important part of using the energy principle here in this scenario is that we need to measure the change in those energies. Here, each of the changes are coded. The standard definition of delta is used here, the final state minus the initial state. We can finally run our code. Here's what that looks like. The red ball is our mass in real life, while the blue ball is our predicted model which we just created. On the graph, the yellow line represents total energy, the blue represents the change in kinetic energy, and the red represents the change in spring potential energy, and the green represents the change in gravitational potential energy. Now, one of the questions posed for the lab was the energy principle satisfied? Ironically, on the graph, as you can see here, the energy principle does not seem to be satisfied. According to our principle, our delta E, or change in energy of our system, has to equal 0 because we have no other objects that weren't included in our model that are doing work on our system. Therefore, the yellow line on our graph should have been a constant 0. But you see bumps. We see bumps. Instances where our energy principle is not satisfied. Is something wrong with our principle? Did we just break the laws of physics? No, of course not. The issue does not lie within our energy principle, but instead with our delta T, or change in time step. The energy principle relies on the idea of constant force in order to be satisfied or held true. Our delta T is actually too large. Because of this, the time step between each iteration in which we calculate our forces is too large, and therefore our forces are actually not constant. This explains our discrepancies. The second question has to do with the periods of x coordinates and the y coordinates. They are different. This is because the second question has to do with the periods of the x coordinates and the y coordinates. They are different. This is because our system experiences different forces on the x and y axis. On the x-axis, the system only experiences the x component of the spring force. On the y-axis, the system experiences both the force of gravity and the y component of the spring force. The axes are unequal in terms of forces experienced, which then explains why the two periods are asymmetrical. Alright guys, that's it. Thanks for watching.